students. We are here for Narayan's dissertation defense, and the rules are that during the first part, this is our public session, you're welcome to ask him questions during his presentation and afterwards. And once we're done with the public session, then the committee will work with him for a while as well separately in a closed meeting. So, Narayan.
Thank you, Dr. Arnott. Good afternoon and welcome everybody. I'm presenting you my PhD defense. And here's the title: Thermal Infrared Radiative Forcing by Atmospheric Aerosol. Just a quick survey. How many of you don't know thermal infrared radiation? Few of them. What about radiative forcing? And finally, atmospheric aerosol. Okay, don't worry. I'll cover these terms as I go along. I'll be presenting you the following items: basic definition and acronyms, aerosol effects on climate, motivation for my work with IPCC report 2007, instrumentation, radiative transfer models, and case studies of different days in Reno, and analysis of aerosol infrared backscattering effect on long wave radiative forcing. Finally, conclusions and suggestions for future work. Let me start with basic definition so that it will be easier for you to follow me. Aerosols, atmospheric aerosols, are the tiny solid or liquid particles suspended in the air, whose size ranges from nanometer to few micrometers. And these are the examples, few examples of aerosols. But I mainly focus on these two types of aerosols: biomass burning smoke and airborne mineral dust. Aerosol optical depth, it measures the total scattering and absorption by the particles in the atmosphere. Thermal infrared or long wave radiation. This radiation lies in 4 through 100 micrometer, and it is terrestrial in origin. So what does this mean? This means the Earth and its atmosphere, as well as every object on the atmosphere, emits the radiation that lies in that range, which we call the infrared or long wave radiation. For example, your body, my body, the ceiling, the walls, everything is emitting that radiation. That's why it is important. And my study mainly focus on the interaction between this radiation, not the radiation that we see, it's the visible, that radiation and the atmospheric aerosols. Shortwave or solar or shortwave radiation, it lies in this wavelength region, and mainly it is the solar origin. For example, the light we see, the visible light, it is a part of the solar spectrum, solar radiation. Radiative flux, I am mainly talking about the long wave radiative flux. Forget about short wave radiative flux during the whole talk. So it is defined as the radiative power incident on unit area, and it is measured in watt per square meter. And we oftentimes convert between these two quantities, wavelength in micrometer and wave number in inverse centimeter, using that relationship. Just keep in mind that relation. And here's a very important term for this talk: aerosol radiative forcing. So this means the effects of aerosol on the long wave radiative forcing, flux, which is measured by that equation, that relationship. Radiative flux with aerosol minus radiative flux without aerosol. So how to realize that concept? Let me demonstrate an example. So do this calculation first. Suppose this is the clean atmosphere. That means we don't have any particles, any aerosols in the atmosphere. And you know, the atmosphere emits thermo-infrared radiation or long-wave radiation and measure that flux on that surface. So you can imagine some number. And next, put some aerosol particle, dust particle, whatever, in the atmosphere and redo the calculation on the same surface and find the difference. So what do you think? Whether this quantity will be the same or different? Just one option. Same or different? I don't tell you the answer. You need to wait until my talk. So if you think this is different, by how much? This is another important thing. Not only on the surface, do the same activity on the ceiling. Here. What does this mean? This is the top of the atmosphere. The surface is called the bottom of the atmosphere and top of the atmosphere. Do the same calculation and find how much is that difference. So that's the whole story of my dissertation and this talk. I will be frequently talking about single scattering properties, SSP, that describe the particle interaction with the incident radiation. And these properties are measured in terms of these following parameters. Extinction efficiency measures how strongly a particle extinguishes the radiation or removes the energy. And it is measured at the sum of the scattering and absorption efficiencies. Single scattering albedo, this term is omega, measures the amount of light extinction due to scattering, which is defined by that equation. Ratio of scattering to extinction efficiencies. Omega equals 0 means all extinction is due to scattering. What does this mean? Suppose this is the atmospheric particle, and this is the radiation coming in, incident radiation. What happens? The radiation might be absorbed or scattered or takes place both. Both things, happens both things, right? So, if the particles doesn't absorb at all scatters, then it's omega equals 1. Omega equals 0 means all the particles is absorbed, nothing is scattered. And here's another term, asymmetry parameter. This gives us idea about the orientation of the scattered wave. So its value lies between -1 and +1. G equals 0 means the scattered waves lies in equally in both forward and backward direction. G equals 1 means radiation is strongly scattered in the forward direction. And G equals -1 is just opposite, scattered in the backward direction. And you have few more terms, back scattering coefficient B and forward scattering coefficient F, which are related by that equation with G. Another very important term is refractive index, which is the intrinsic property of a particle that controls the single scattering property. These properties are controlled by dash quantity. And mathematically is the complex number, and it is expressed as the real part and the imaginary part. Broadly speaking, the real part is responsible for the scattering process, and this imaginary part is responsible for the absorption process. These figures and this information I took from the IPCC report 2013. IPCC stands for Intergovernmental Panel on Climate Change. And from this figure we see that the aerosol affect climate in various ways. The first one is scattering. The aerosols scatter the radiation leading to the cooling effect. And the scatter absorbs radiation leading to the warming effect. These two are called direct effect of the aerosols on the climate. Aerosols also have indirect effect on the climate. The clouds act as a cloud condensation nuclei, CCN, and it allows the formation of the cloud. And maybe you know the cloud has a big impact on thermal radiative, Earth radiative balance, budget. Maybe we are familiar that the cloud strongly scatters the visible radiation, which is the part of the shortwave radiation, you know that, right? And at the same time, clouds strongly absorb the long wave radiation, thermal infrared radiation. And maybe we know that the cloudy sky nights are much warmer than the clear sky nights. This is the reason. I took this chart from IPCC report 2007, which displays the radiative forcing contribution by various agents present in the Earth and atmosphere. Among these various species or components, I am just focusing on two agents, carbon dioxide and aerosol. According to this report, the concentration of carbon dioxide has increased by about 100 parts per million by volume during that period, 1750 to 2005. And this change in carbon dioxide concentration leads to that much amount of radiative forcing, plus 1.6 watt per square meter. And this positive sign means the radiative forcing is positive. Positive radiative forcing means it contributes to the warming or heating effect. Now look at the aerosol component. The aerosol causes the negative radiative forcing. But one important thing to note down here is this includes only the short wave radiative forcing, not long wave radiative forcing. So in that sense, this is not complete. So how big is the long wave aerosol radiative forcing? Here is our measurement. On a typical day in Reno, this value is like 0.4 watt per square meter. For example, if you add this term over here with that term, what will happen? The negativity is highly reduced. And what would be the effect, overall effect? So look at this bottom bar. So the total radiative forcing would shift further in the positive direction. It would increase further. And this leads to the warming, more warming. So that's our main motivation. I mean, we are not supposed to ignore the long wave aerosol radiative forcing in the climate model. Here is an important information to share with you. The Great Basin, that is Reno, lies in that area, is an appropriate place to study dry aerosol climate forcing on a regional scale. Due to the following reasons: the Great Basin observes coarse mode or dust particles almost every day, and these particles offer non-negligible long wave radiative forcing. This area occasionally observes heavy smoke from California wildfires and dust storms during summer and late spring due to its hot and dry conditions. Finally, due to generally low humidity, it is easier to model dry aerosol and reduce humidity-induced uncertainties on aerosol optical and radiative properties. These are the instruments that we use to measure the aerosol properties as well as emission from the atmosphere. The very first instrument is the Fourier transform infrared (FTIR) spectrometer, and it consists of various external and internal components in it. And the main purpose of that instrument is to measure the spectral intensity or radiance of the long wave radiation emitted by the atmosphere. These two are the solar based instruments. This one is multi-filter rotating shadow band radiometer, MFR-SR, and this is AeroNet, Aerosol Robotic Network, CML sound photometer. The basic idea behind this instrument is just to measure the direct and diffuse solar radiances, and based on this information we can derive the aerosol optical properties. And the picture on the right is the National Weather Service radio sound. This is the balloon, and this is used to measure the atmospheric profile such as temperature, pressure and relative humidity of the atmosphere, and it is launched twice a day, and there are many radio sound stations around the world. And one important thing, we use the atmospheric profile measured by the radiation in our models. Rate transfer models, it is the heart of our work. So basically there are two models, LVL-RTM, which stands for line by line radiative transfer model, and this is a gas model. And next one is LVL-DIS, discrete ordinate radiative transfer solver. It's aerosol model, and it has diode in it. Sorry, this is diode, and LVL-DIS is a combination of LVL-RTM and diode is that thing. And LVL-RTM uses the atmospheric state from radio sound, as I mentioned, and spectroscopic database from such as Hytran as an input to output simulated clear sky radiance spectra as well as gaseous optical depth profile. And this input is used for the LVL-DIS. This requires bulk scattering properties, bulk single scattering properties of the aerosols, which are computed using the Mie theory based on the information on refractive indices of aerosols and aerosol size distribution. The final input required for this model is the parameter file that controls the execution of that model. And finally, it outputs the simulated radiance and spectral flux spectra. Remember, these two models uses the multi-layered plane parallel atmosphere to output those things, where T and P represents temperature and pressure, and this term tau represents the optical depth in each layer of the atmosphere. Aerosol size distribution. The aerosol size distribution are commonly represented as a combination of log normally distributed components, which is given by that equation. This is the volume size distribution. This I represents the number of modes. In our case, we use n equals to 2, which represents the bimodal log normal distribution. And C is the total particle volume per unit area. This sigma is the standard deviation. R is the radius of the particle, and Rm is the median radius. And based on this equation, we have two size distribution for different events, smoke and dust event on that day, 26th August and 24th April. And what we see here, the smoke, in each smoke event, the fine mode, that means the particles that are less than 1 micron, heavily dominates over the coarse mode. The coarse mode are the particles that are greater than 1 micrometer. In contrast, in dust event, the coarse mode particles heavily dominates over the fine mode. And these are the parameters used to compute these size distributions. So this is the very important properties I mentioned, and this is the complex spectral refractive index of the biomass burning smoke, and this is for a mineral dust called kelonite. And this blue line represents the real part, and the red one is the imaginary part in both plots. And we use that refractive index to model our fine mode aerosols, and this refractive index to model our coarse mode aerosols. And one important thing, the absorption coefficient is related to the imaginary part of the refractive index by that equation. That means as the imaginary part increases, the absorption coefficient increases. Radiative transfer equations. So this is the main radiative transfer equation that the D-Short algorithm solves for the plane parallel atmosphere, where mu is the cosine of the angle theta, where theta is the zenith angle, and phi is the azimuthal angle, and J is the source function, which consists of scattering and thermal emission source function. This first part represents the thermal emission source function, and second part is the scattering source function. And this equation can be used to compute both the upwelling, upward going, and downwelling radiance. So up arrow means upwelling, down arrow means downwelling. And these quantities are used to calculate the upwelling and downwelling spectral flux using these equations. And this spectral flux can be used to obtain the broadband flux by integrating over the desired wavelength region. And finally, this is the radiative forcing at the bottom of the atmosphere. BOA means bottom of the atmosphere, and this is for top of the atmosphere, TOA. Here is a case study of a clear sky over Reno. We measured the long wave radiation, thermal infrared radiation emitted by the atmosphere in Reno on August 1st, 2013, at that time, 17 LST. And this is the green curve, and the red curve is the corresponding simulated spectra using LVL RTL model. Radiance plot, we can have a lot of information regarding the absorption and emission bands and their features of many greenhouse gases. For example, this is the absorption and emission bands of the water vapor, and this is also for water vapor. And this is the carbon dioxide strong absorption and emission band, and this is the ozone band. And the region from 800 to around 1300 is called the atmospheric infrared window region. And this second plot shows the difference between the measurement and simulation. So there is a big difference between the measurement and simulation, especially in that region and that region. This is the water vapor absorption region. This may be associated with many things. For example, mainly the variability of water vapor in the atmosphere, because the water vapor profile right in the measurement site and the radio sound site can be quite different. And this region is associated with several factors such as FTI calibration error and errors in the water vapor continuum model, as well as the other main important thing would be the aerosol effect. Because, as I mentioned, this is the gas model, and it doesn't account of the aerosol effect. That's the reason. Next, I present you a case study of California Rimfire event in August 2013, last year. So I think most of you are familiar with that event. We had a big smoke in Reno, right? So it was the third largest wildfire in California recorded history. And this is a satellite image of the rim fire. We clearly see that a huge smoke is moving toward Reno. Here, this is the Lake Tahoe here. And this is the picture of the smoke haze from the rim fire hanging over Reno. And the visibility is highly reduced. Our next interest is to see the direction of the air flow during that event. For that purpose, we used the NOAA high speed model. And we carried out a 48-hour back trajectory analysis of the air mass flow at 3 different levels: 500 meter, 1 kilometer, 3 kilometer. And all these model results so that the air was flowing from southwest towards the Reno. And we can say that this airflow could transport this smoke plume all the way from Rim 5 to Reno. These are the CML observed shortwave optical properties during Rim 5 on that day, 26th August. CML observed very high aerosol optical depth on that day, which indicates the presence of large amount of particles in the atmosphere. And even in the late afternoon, around 5 p.m. local time, it further increases. Maybe it indicates the arrival of another fresh smoke in the smoke flow. Now the question is this aerosol optical depth is due to small particles or big particles? That's the question. This is answered by this another optical parameter, which is called angstrom exponent. It is derived, calculated using that equation. So this term is the aerosol optical depth at 440 nanometer, and this is the same thing as 870 nanometer wavelengths. And the angstrom exponent, if this is high, I mean if less greater than say 1, this means this indicates the presence of very small sized particles in the atmosphere. So this indicates the presence of small sized particles in the atmosphere, which is further evident by the size distribution plot. So you see the fine mode particles dominates over the coarse mode particles. Now these are the asymmetry parameter and single scatter albedo for the smoke event. This is the asymmetry and this is the single scatter albedo for fine mode. And these are the same quantities for the coarse mode and bi modes. See, the red is the asymmetry parameter and the blue is the single scatter albedo. In overall, what we can say, both parameters are the function of the wavelength or wave number. And next thing is the asymmetry parameter in general increases with a decrease in wavelength. But the single scattering albedo is a strong function of the refracted indices. These are the efficiencies of the aerosols during the smoke event. This is for fine mode, coarse mode, and then bi modes. In each plot, the black represents the extinction, red represents the scattering and absorption, blue represents the absorption. In the fine mode, the scattering absorption is very, very low. And this means the extinction is mainly due to absorption. But if you look at the coarse mode, both scattering and absorption are significant and both contributes to the extinction. And the bi modes, the efficiency of the bi modes closely resemble the features of the fine mode. Why this happens? This is because the fine mode was a dominating mode for that case. And these are the spectral radiative forcing by aerosols during the fire event. This is the bottom of atmosphere radiative forcing for different modes, fine, coarse, and then bi modes. And this is for the top of atmosphere. So we can make some conclusion based on this plot. The radiative forcing is really strong in that region, right? So which we call the infrared window region. Just pretty strong. But these values are pretty low or negligible in the water, strong water vapor absorption and then strong carbon dioxide absorption. And the BOA forcing is much larger than the TOA forcing in that region. And these were calculated based on these equations which I already mentioned. Now we calculate the broadband radiative force from the spectral forcing based on that equation. In this case, I am interested to see on these values because we are talking about the fine mode smoke particles. So these are the contributions by that particles. Now the question is, are these values big or small? Number one, if small, are they ignorable, negligible? So to answer that question, if you remember the results from the IPCC report, it said the radiative forcing due to increase in CO2 concentration in more than 250 years, 1750 through 2005, was 1.6. So as compared to that result, this value, which is the top of atmosphere, both are top of atmosphere, is not small. Even it is small, you can say small, but not negligible. That's my conclusion. Now I present you the case study of dust storm event in Reno that took place on 24th April 2013. Our instrument observation validates the occurrence of that event. So this is the CML observed aerosol optical depth. The optical depth suddenly rises around 2 to 3 p.m. local standard time, which could mean that there's something going on. There are some particles. There are a lot of particles. The particle suddenly increases in the atmosphere of Reno. Now the question again is this optical depth is due to small particle or big particles? Now this is further answered by this parameter, angstrom exponent. What do you think? Is small or big? So look at the same time, 2 to 3 p.m. LST, the angstrom exponent suddenly drops. Low value of angstrom exponent is big size of particles. So coarse mode, presence of coarse mode particles. So if you look at the MFR observation, it also shows the similar features for the aerosol optical depth and angstrom exponent. This is further evident by that side distribution. So the coarse mode particles dominates over the fine mode particles. Now, our next interest is to see the source of that dust, where it came from. That's in our interest. So, to fulfill our interest, we again carried out or used NOAA high-speed model, as I did in the fire case. So this result is different from the last one. See, the direction of the airflow is from northeast this time, coming to Reno. And we assume that this airflow transported the dust particle all the way from Humboldt Sink to Reno. This is our best guess. We also followed every step as I did in the fire case. And this is the spectral radiative forcing due to these various modes during the dust event. This is the BOA radiative forcing and this is the TOA radiative forcing. We again see that the radiative forcing is strong in this infrared window region. Again, we see the strong radiative forcing in the water vapor absorption region. This is the unsaturated water vapor absorption region here. And see, the radiative forcing due to fine mode is very, very small as compared to these rest modes in both cases. And again, the BOA forcing is much larger than the TOA forcing. And these are calculated using that equation again. Just recall. Next, we calculate the broadband radiative forcing with that equation. This time we are interested to see the radiative forcing due to the coarse mode, which is related to the dust particles. Now, this is 5, 1.7. Are they small or big? In terms of long wave radiative forcing, these are not small. These are pretty big value number. So here is our conclusion. Coarse mode mineral dust aerosols, which are highly absorbing and scattering, as I showed in the extinction efficiency plot. These have significant positive radiative forcing, and they contribute to the warming effect. Now, I'd like to compare our results with the published results by Sicard and others in 2014. These are the results. This is the BOA radiative forcing, this is TOA radiative forcing. And based on these results, we can draw that conclusion. And these are based on 11 dust outbreaks observed in Barcelona over that period. Our results are consistent with these results, despite several degrees of freedom. Number one, mineral dust model, including refractive index, side distribution, concentration, etc. Surface temperature, relative humidity profile of the atmosphere, spectral range, radiative transfer model used to compute radiative fluxes, etc. These are the variables that can be different between theirs and ours model. Now, here is an analysis on an aerosol infrared backscattering effect on the long wave radiative forcing. For this purpose, we consider two different types of aerosols. The first one is scattering and absorbing, and next is scattering only, that means no absorption. So how do I do that? For that part, I simply use the coarse mode aerosol from the dust case. So everything is done already. I already displayed the results, so I don't need to worry about that part. So how do I model the scattering aerosols? Very simple idea. I simply put the imaginary refractive index or set refractive index to very low value, so that the aerosols becomes only scattering, no absorption. And I compute both bottom of the atmosphere and top of the atmosphere radiative forcing, and I compare these results with that results. And here are our conclusions. The aerosol backscattering effect contributes as much as 67% of the total forcing and 58% of the total forcing at the TOA. The aerosol IR backscattering effect significantly contributes to both the BOA and TOA infrared radiative forcing, even if the aerosol do not exhibit absorption at all in the thermal infrared. So many people can think that this is due to absorption, not only absorption. Scattering also plays important role to increase the radiative forcing by the aerosols. Now, as a final part of my calculation, I compute the aerosol longer radiative forcing on a typical day. So we did the fire day, we did the dust day. Now we want to see how the value look like on the typical day in Reno. For that purpose, I use that side division and that sounding profile, atmospheric profile, and these are the results for the BOA and TA radiating forcing. Look at the values for the typical day. Are they small or big? Looks small, but they are not negligible. So here is a conclusion. Even on a typical day, Reno absorbs significant radiative forcing due to coarse mode aerosol. Now these are my conclusions. Okay, good.
Why is a typical day?
Good question. Why do you think typical day?
I don't know. It's a day next to a dusty day, so.
Yeah. This was just right before the dusty day.
Yeah.
But their case, we didn't have any fire, we didn't have any dusty storm. That's the typical, that's usual day. That's how we call it typical day.
Could we have like a stagnation of aerosol from the day above? From
What
the
is
day before, like some aerosol from the coarse mode could still alive in Reno due to the dust the previous day.
It could be, but most of the time we observe the coarse mode aerosol in the Reno's atmosphere.
Yes, it's like the size distribution, even though it's a typical day, the coarse mode is quite high, higher than the fine mode.
Yeah. So this indicates the presence of large particles.
Yeah.
And it doesn't make any difference what time of year, correct? Because of a typical day in winter, because of the lower humidity, and does that cause less coarse?
Yeah, there are different things that that what is called that can remove the dust particles in the atmosphere. Just like precipitation, you have precipitation, then it is washed away. So it might be different on the atmospheric condition like that, or meteorological condition. Does that answer the question?
Yeah.
Okay.
Yeah.
Here are my conclusions. We studied the thermal infrared properties of the greenhouse gases, biomass pouring smoke aerosols, and mineral dust aerosols, along with aerosol IR backscattering effect on the radiative forcing. The long-wave radiative forcing due to aerosols is significant and positive, which produces warming effect and contributes to partially counterbalance the strong aerosol cooling effect in the short-wave region. Based on that information, the inclusion of accurate infrared radiative forcing by aerosols is vital to the climate models. The Great Basin of the United States can be appropriate place to study the dry aerosol climate forcing. The general long-wave radiative forcing of the aerosols is associated with not only absorption but also scattering. And aerosol long-wave optical and radiative properties likely possess a substantial uncertainty due to uncertainties in the aerosol properties due to their very complex structure and highly variable characteristics over time and space during transport, uncertainties in the vertical distribution of aerosols in the atmosphere, lack of local and regional data of the aerosol properties in the long-wave spectral region, errors in the visible optical depth estimates. And these are some suggestions for the future work. Very few studies have been carried out in that field related to the topic of that dissertation. That's why more studies is required in that field. Complete understanding of the regional aerosol long-wave radiative properties help us to incorporate our results into climate model simulation with confidence. Long-wave impact of sea salt, coarse mode aerosols should be studied very closely, especially in windy regions, to accurately account of the sea surface temperature by infrared sensing from satellite. Now, I would like to appreciate following people. First of all, I would like to express my sincere gratitude to my advisor, Professor Dr. William Patrick Arnold, for his encouragement, support, and regular guidance throughout the project. I would like to thank committee members, Dr. Klein, Dr. Weinstein, Dr. Pinsky, and Dr. Mitchell for serving on my committee and their advice to make my dissertation better. I appreciate Department of Physics at the University of Nevada, Reno for their financial support and providing me an opportunity to pursue my career. I would like to thank faculty, staff, colleagues, and friends at UNR, as well as in the Reno community, for their direct and indirect support, as well as friendship. I am thankful to Atmospheric and Environmental Research AER Radiative Transfer Working Group, especially Dr. Alvarado and Dr. Pereira, for helping me with the LVL RTO model. Similarly, I would like to thank Dr. Turner and Dr. Merelli for helping me with LVL DIS model. I would like to honor my wonderful wife Cheryl and two lovely sons, Vision and Angelus, for their patience and cooperation during the project. They are at the back. At this moment, I like to remember my parents and grandparents back in the middle. They are in fact a great source of inspiration for my every single academic achievement. I am thankful to them because they sent me to school. There are some inspiring moments. You see my grandpa praying for me right before my departure to the United States. And on the right, my mom is feeding me yogurt, wishing for safe journey, good fortune, and success in mission audit. Also, it is my pleasure to remember my lovely home village and high school where I was born, grew up, and started my education. Finally, I'd like to share a few things with you at this moment. The first one is, I'm working on the draft to get those results published. Second thing is, I feel both sad and excitement during this moment. Excitement about my academic achievement, and I'm completing my formal education as a formal student. And sadness in a sense that I'm going to miss my wonderful formal student life. Anyway, thank you all for your active participation.
Thank you, Narayan. Questions, comments, thoughts?
Top of atmosphere, I didn't catch what the altitude was for that.
That's another good question. So there is no, definite line for the top of the atmosphere. But in our case, we use 75 kilometers at the top of the atmosphere. So which extends as high as stratosphere.
So now the balloons that you used here measured that up twice a day.
I'm not sure whether this can go as high as that height.
There was another question I had on the graph during the fire. There was that one drop. Was that due to a glitch in the computer getting the data, or was that actually a drop and was it a clear spot just that time of day?
This looks like a snapshot.
No. It was your graph
Go back to the
on the fire section.
rim fire part.
Yeah, your angstrom reading. Next one on your right there.
Okay.
Drop.
This one. That's a good question. Yeah. So this indicates the large size particles anyway, right? This is a low value. And our best assumption is, the cloud passes right over the instrument at that time.
Okay.
I don't know. I'm not sure.
Okay. That's what I was kind of curious. I was like, well, that's a good drop. Just.
Yeah. Good catch. Good notice.
Yes, Heather.
So I have a question similar to like the top of atmosphere question. How does the vertical distribution of PM concentrations impact the results from the CMO?
Can you repeat the questions?
So when you're using the CML to collect AOD, what's the vertical path, I guess, of the sensor? So is it considered the surface to what you're calling the top of atmosphere? And how does the vertical distribution of PM concentrations impact that data? It's okay. It's okay if you don't know the answer, I'm just curious.
So I'm not sure about that question actually. So you mean if you had more fine particles on that day?
So back to like Marcelo's question about the coarse mode potentially being aloft. So if you have your CMIL on the ground and you're quantifying aerosol optical depth, and you have a high concentration of coarse mode aerosol aloft, so let's say it's above the convective boundary layer potentially?
No, I don't think so.
It doesn't impact the results at all? Okay.
The aerosol particles are likely to distribute as high as around 3 kilometers and so on.
So her question is, what if you had a layer, so instead of having a layer of aerosol close to the surface, if you raised it to here, or here, or here, would you get the same answer, or would you get a different answer?
Okay, yeah. That's the question, right?
Yeah.
Okay, so let me explain a few things. This is a very kind of vague question. So let me explain something. Is clear here?
Yeah. Thank you.
So this is the ground, and we are assuming the dust layer up to that level, right?
Yeah.
And then what happens, this is the emission from the ground, and the particles here, they just scatter back and then emit back to the atmosphere. And that's why our radiative forcing at the bottom of the atmosphere is increased. But if you assume that that particles in that layer, the effect would be very low, because there are two things. The first thing is, if the particles is here and the temperature is low, right? Low temperature means low emission. And the contribution by the aerosols to the emission is low. And that's why we have less radiative forcing in that case.
So then the question I think also was with the CML, or say like this retrieval, does that depend critically on the layer, whether it's here, here, or here? Is that? what
Yeah,
else
so
would be
basically,
out?
I think what you're showing me on the bottom is the distribution, the size distribution at the surface? Is that correct, or is that the size distribution?
Oh no, this is the over the whole body of
Over the
ball.
whole volume?
Right above the instrument.
Okay.
Yeah.
And so if there's layers like you drew on the board, does it impact any of the CML results, or does it matter? It's all just, you have to assume a homogeneous layer of mixing, I guess. is my
Yeah.
answer. You do?
Yeah.
Okay. So it will impact your results?
Yes.
Okay.
Right.
Thank you.
What are the input parameter of your radiative transfer model?
What is that in?
Input parameter of the radiative transfer model.
Input parameters. Which radiative transport we are talking about? LVL-RTM or LVL-DIS?
The first one.
The first one is the atmospheric state from the radio sound, the balloon sounding, and this measures the temperature, pressure, and relative humidity. These values, and then it uses the spectroscopy database. So this means this is the line absorption parameter for the gases. So which is usually taken from the HITRA. This is already compiled in the HITRA database. So this is very complicated thing. So we just use that, and then LVL-RTM directly can use that. We don't need to worry much about that.
Mike, can you go to the IPCC slide?
Okay.
Those results come with onshore radiative.
Right.
And how about your result? Have you calculated the onshore radiative on the radiative forcing?
No, that's a good question. So I actually want to think. I also actually think about that things, but the problem is there are a lot of variables. So there are several variables. For example, there can be uncertainty in the measurement of the aerosol optical depth. We borrow the optical depth of the visible region. There can be one uncertainty, and we use the refractive index. And there can be another uncertainty in the refractive index, and the modal uncertainty. So I don't know. I'm not sure about that, how to include those kind of things. And I think this error bar here represents the level of confidence. So short error bar means the people are.
How do you calculate level of confidence?
Yeah, maybe it depends upon the various published results they are using for that purpose. So I don't know in detail viewing that.
So along that same, in 1750, who was collecting the data and where? Because I mean, it's like, well, if it was over there in the Mediterranean and Italy, it's a lot different than it would be here in Reno. So we don't know what that result. We don't know what the numbers were in Reno back in 1750.
Interesting. So maybe I don't know. I'm not quite sure about that. But my best guess is they can somehow interpolate, extrapolate. Somehow they can guess. I don't know.
Is this for the top of the atmosphere or the bottom?
Top of the atmosphere. Usually they do it for the top of the atmosphere.
And you said it's lower in the top of the atmosphere, right? The radiative forcing?
The radiative forcing is small as compared to the bottom of the atmosphere, because we are assuming the aerosol to reside nearby the surface.
How big do you think is your uncertainty during the course day, during the dusty day, due to the meat theory inside the model instead of an S-spheroid model?
Don't know.
You don't know? Is there any
No,
possibility?
I don't know any uncertainty about that.
And can you increase, how difficult it is to change from a spherical model to a spheroid model?
Yeah, this is the usual question, a common question I mean. So we are using mean theory, which is applicable to the spherical model, right? But the first thing is, at this time we don't have any option. So we don't have any idea about the actual morphology or shape of the particles. And then this is the simplest model we can use. And the next thing is, this does not so dangerous because we are working on the thermal infrared long wavelength region.
Okay.
And then we are dealing with small particles, and for the small size parameter it won't be that much big difference. It will be acceptable, I guess.
Yeah, with water clouds, the short wave dominates over the long wave, so you have a net cooling effect. And here you're showing that the long wave almost cancels out the short wave. So how do you explain that?
Here?
Yeah, right there.
Yeah, that's another good catch, because this is just the illustration. Because this is, the point for watt per meter square is not the global mean. The important is not the global mean, this is the local mean.
Yeah.
And if we have, you have similar kind of things over all around the world, and then it is pretty big, and it tends to, cancel. It is not just, it just try to counterbalance the negativity of the short wave radiative force.
But also you have absorption in the window region,
Right.
and that might be a factor.
You have just water vapor.
Yeah. Well, water vapor doesn't absorb in the window region, but the aerosols are, right?
Yeah, right.
Right.
Yeah.
And that might contribute to that.
Yeah, that. But yeah, definitely.
Okay, let's see. Who else has a question?
Just a comment.
Yeah.
It might be useful to look at the IPCC report, because I think, particularly with dust, they've tried to find out what the dust loading was in 1750 versus 2005 and figure out what the anthropogenic contribution to dust loading is. I vaguely recall that, and it might be useful for this study to try to ferret out what the anthropogenic component really is.
Yeah.
And then the important thing is the data available for the long wave region or not?
Yeah, I know.
That's important.
Yeah,
Right?
but a loading of dust is going to be a loading of dust, and if you figure out the loading of dust, it won't matter.
Okay. Going once. Anybody else? Okay, thanks everybody. Thanks.